Okay, we're going to go over the chapter 8 homework. Okay, so chapter 8 homework says look at the table of values for the two variables. Which relationship is linear? Which is exponential? Explain why. Okay, so as we're looking at these, we want to look at the change that's happening in the y values. So when I'm looking here, this jump of 220 to 70, if I find the difference there, that's 150 is the jump. Okay, then if I look again at this jump here, 370 to 220, if I subtract those, I'm getting 150. Okay, if I go here again, okay, 520 and 370 is giving us 150, and this next jump again, 670 and 520 gives us another 150. Okay, so I see that this one, because it is a steady jump rate, this one is going to be linear. Okay, now when I look at the next one, here it's increasing by 70, here it's increasing by, it looks like 140. Okay, the next one, it's looking like that's an increase of 280. And then the next one, it's looking like when I subtract those numbers, it's an increase of 560. So you see how the amount, it is increasing continuously over time, but this increase is growing, like the amount of increase is actually changing. It's getting bigger and bigger and bigger and bigger. So this one is going to be your exponential function. Okay, because the amount of increase grows. And this one is linear because the amount of increase stays the same. Okay, another way we can describe that is the amount of increase is constant. Okay, it's a constant increase. It's always the same amount. Okay. All right, let's go down to the next part. Okay, so it wants us to find y hat when x equals 2 for each of these. Okay, so I'm going to go ahead and plug in here 2 to the second power, right? And so I can go ahead and simplify this. 2 to the second power is 4. So this will give me 12 times 4. 12 times 4 is 48, right? Okay, let's go to part B. Okay, we want to know what y hat is when the x value is 2. So again, 12 times 2 to the negative 1 power. Okay, remember when you have something to a negative 1 power, that's basically putting it into the denominator. So this becomes 12 over 2, which is 6. Okay, for part C, we're getting y hat equals, I believe there's a decimal point there and a decimal point there. Okay, 12 times 1.5 to the second power. Okay, so I'm going to go to Desmos to help me with this. So 12 times 1.5 raised to the second power. Okay, and that's giving me 27. Okay, all right, and then the next one is going to be part D. Y hat is equal to 12 times 0.5 raised to the second power. So let's go ahead and put that into Desmos. 12 times 0.5 raised to the second power. Remember, if you're not sure how to get that exponent up there, okay, you can go to your keyboard and hit this A to the B button, okay, and that's going to move it into the exponent for you. Okay, so when I do that one, I'm getting that y hat is going to give me 3. Okay, so I'm just evaluating those. All right, let's go ahead and look at this next one. Okay, it says bacteria, an exponential model describing the growth of a laboratory culture is that the population, the expected population, equals 500 times 1.06 raised to the day. Okay, how many bacteria did the lab culture start with? Okay, so remember, the starting point, we're gonna call it like day 0, okay, where that's the beginning, okay, and so when we raise this to the 0 power, okay, we get 500 times 1.06 to the 0 power. Well, anything to the 0 power is 1, so this is really 500 times 1, so they just started with 500 bacteria. So this number right here actually tells us the starting point, but if you're wondering how we got that, it's because in the beginning we say we were at 0 days, okay? So next, what is the growth rate, okay? So the growth rate is told to us by this number here, okay? This number is 1.06. We think about our growth rate as a percent, okay? So 1 meaning the whole, and we're looking at anything above the whole, okay? So by subtracting 1.06 minus the whole, which is 1, we can find actually the amount of increase, which is 0.06. And if we change this into a percentage, remember, by moving the decimal twice, we're getting 6% for our growth rate. Okay. All right. Next, part C. Okay, it says how many bacteria should the lab expect there to be in a week? Well, a week is 7 days. So let's go ahead and plug this in. So our expected population is going to be 500 times 1.06 raised to the 7th power. Okay, now I'm going to go ahead and go over to Desmos to help me with that. Okay, so in Desmos I get 500 times 1.06 raised to the 7th power. Okay, and here's what I get. I'm going to go ahead and round that to the nearest whole number. Okay, so my nearest whole number that I would be getting would be about 752 bacteria. Okay, so that's what I would get there. All right. Okay, let's take a look at the next one. So it says residuals. Suppose you have a fit model to some data. Now take a look at the residuals. For which of the following possible residual plots would you reject your model? Why? Okay, so if I'm seeing residual plots that are creating a bend or a curve like this one here, this is probably telling me that my linear model is not going to be appropriate, okay, or my model I have is not going to work. So I'm going to choose B, okay, and I'm choosing B, and because there is a curve or bend in the residuals. Okay, all right, let's take a look at the last one. And these go together. Okay, so this is GDP. The scatter plot shows the gross domestic product GDP for the United States in billions of dollars plotted against years since 1950. So here's our dollars, here's our years. The graph is going up over time. Okay. Okay, so when I look at this, okay, first question says, does it appear that we could use a linear model? So looking at this, I mean, possibly, I could possibly fit a linear model there. Okay, so I could possibly fit a linear model. So for part A, possibly could use a linear model. Now, when I'm looking at this though, when I kind of draw just a rough sketch of a line, you see that a lot of the points are a little bit far. There's a little bit of a bend here. You know, we could use a linear model, but my guess intuitively is that that it's likely not going to be a linear model. Okay, but let's go on to part B. Okay, it says here's the scatter plot of the residuals. So here are the residuals. Okay, now do you think there is a good that is a good fit for these data? Explain why. Okay, so these are the residuals if I best fit a linear model, okay? And so what is this telling me? Well, these residuals are clearly a curve, right? And so this is telling me a linear model is not going to be a good fit, okay? So whenever we have residuals that end up showing a clear curve, okay, it's that, yeah, the linear model is not going to be the best fit, okay, and I probably want to go in and check maybe an exponential model and see what those residuals end up looking like, okay. We want them to look a little more random, something like this, maybe even something like this, right? But we definitely don't want to see this curvature pattern, okay? And you guys are going to need to finish the vocab and the what can go wrong on the back on your own, okay?